Hello everyone, welcome to the second installment of our fall lecture series. So today we are excited to welcome Alexia Kubas, who is a PhD student here at Cornell. Her research is with Dr. Brittany Schmidt and largely looks at icy landforms called pingos to learn about how ice and groundwater might shape planetary surfaces. So today she's going to talk a bit about analog studies to better understand how water and life might behave on icy worlds across the solar system. So please join me in welcoming Alexia, and I hope you all enjoy.
Thank you, Alina, for that introduction, and thank all of you so much for being here tonight. Alina knocked it out of the park with the brief synopsis of what this talk is going to be about, but I'm super excited to share my love for analog science with all of you tonight and hopefully teach you how we can turn to our own planet to learn more about other planets in the solar system. So, I'm sure that analog is a word that is in most of your daily vocabularies and you've interacted with it before, but just to start us all off on a clean slate, I thought I would bring up the definition of an analog from the Merriam-Webster dictionary. So, an analog is something that is similar or comparable to something else, either in general or in some specific detail. And today I'm specifically going to be talking about analog environments. And if any of you have engaged in pop culture at all in your lives, this should be something that's very familiar to you. Who in here has seen Star Wars, Interstellar, or Dune? Yeah, almost everyone. So something about, these are great movies, right? Amazing movies. Unfortunately, the people making these movies are kind of poor and they can't afford to actually shoot on location. So they have to turn to places on Earth that look and feel otherworldly so that the audience can kind of suspend their disbelief and make them feel like they're actually on another planet with the characters. So Star Wars, a lot of the scenes take place on the desert planet of Tatooine, and every single Tatooine scene was actually filmed in Death Valley National Park in California. So the top left here shows Luke Skywalker walking at his home on Tatooine, and the bottom left shows Death Valley National Park, which is where this was filmed. And Death Valley has everything. It has the rolling sand dunes, it has mountains in the background, it has everything but the two suns on the horizon, which is why we have CGI. And one of my favorite pictures is here on the bottom right. We have C-3PO shaking hands with a Death Valley park ranger when they were shooting scenes for Star Wars. And you can actually go to Death Valley, and there's a very popular tourist attraction where a very famous scene was filmed where C-3PO and R2-D2 are kind of in a little spat, and they're walking along the beautiful landscape of Tatooine, but it's actually Death Valley. So here's the scene that I'm talking about. Oh, unfortunately, it looks like we don't have audio on here. But anyway, they're fighting. C-3PO is walking off in one direction, R2-D2 is going the opposite direction. This was all filmed in Death Valley, and it's a very popular tourist spot. You can go there and stand on the very dune where those two robots stood themselves. But the great thing about our planet is not only does it have desert landscapes, but it also has regions that can make you feel like you're on a frozen, desolate world. So the movie Interstellar, one of my favorite movies, it's about Matthew McConaughey is an astronaut who is sent off with a team of their astronauts to explore the universe for other planets that might be habitable for humans, because unfortunately their home planet of Earth was ravaged by climate change. Thank God that this is a science fiction, we don't have to worry about that in real life. So there's one part in the movie where they go visit this icy world, and here's a beautiful still from this part of the movie. This was actually filmed entirely on Svinnafellsjökull Glacier in Iceland. And if you want to go see it for yourself, you can travel there just like these really cool travelers. You just have to make sure that you watch out for those crevasses in the surface, because you don't want to fall down those. That'll be bad news for you. I think that might have happened to Matthew McConaughey in the movie, but I can't quite remember. And then going back to the desert, recently, there have been 2 new installments of Dune, which these are definitely my favorite space movies out of the bunch that I've shown you so far. And for those of you that aren't familiar with Dune, most of it takes place on the desert planet of Arrakis. The cinematography in Dune is beautiful, and the landscape definitely does a lot of the heavy lifting. So all of the Arrakis scenes were either filmed in Wadi Rum, Jordan, or in the Liwa Oasis in Abu Dhabi. But these analog environments aren't just pretty locations for movies that can make us feel like we're on another planet. They also have a scientific use. So scientists use analog environments on Earth to study processes that are occurring on inaccessible, extreme planets in the solar system. And analog science is awesome because while we're learning more about what might be happening on other planets, we're actually answering unresolved questions about how our own planet is working. So if we go back to Death Valley, for decades now, it's been used as a testing location for Mars rovers due to its very similar geology and terrain. So this middle picture here shows a Mars test rover for, I believe, Perseverance. Back in 2012, they were testing the wheels to make sure that the rover could navigate and function okay in this desert environment. And in the bottom right here, we have Cornell's very own Carl Sagan visiting Death Valley back in 1980 to test a model of the Viking lander. And you might think that this top picture is a beautiful landscape of Death Valley, but no, this is actually an image that a rover took of the surface on Mars, but it looks just like a desert we would have on Earth, which just goes to show why JPL engineers have loved driving those few hours into the desert to test their rovers on. But Death Valley isn't only a good Mars analog because of its terrain and the sand dunes. It's also a great analog for ancient Mars because Death Valley is home to hyper-arid fluvial environments, which are very similar to things we see on Mars. So shown in the background here, and the foreground, is Badwater Basin, which, fun fact, is the lowest elevation point that you can go in the continental US. Now, most of the year, it looks like this, so it's covered with salt flats. And the reason they're there is because thousands of years ago, Badwater Basin was filled with a lake called Lake Manly. And since Badwater Basin is a very low-lying region, rainwater would basically spill into this basin and bring a bunch of salts and minerals with it. And Lake Manly didn't have any outflow path, so the water just got stuck there. And since it's such a hot, dry environment, all of that water ended up evaporating away and leaving the salts behind, and it's still there. And Mars has very similar locations to Badwater Basin. A famous one is Jezero Crater, which we actually have a Mars rover there digging around and looking for really cool astrobiology relevant minerals and just trying to learn more about ancient Mars and what the surface was like. So, in 2024, Kalucha et al. Collected samples at Badwater Basin and analyzed the organic carbon content of the samples as an analog for similar samples on Mars. And like I said, most of the time Badwater Basin looks like this in the background, very dry, only the salt flats. But this is me and some of my friends and colleagues. We were in Badwater Basin in spring 2024 for a class we were taking here at Cornell. And we just so happened to go when Badwater Basin was flooded, which was really fun to see. But anyway, Kalucha et al. Found that organic carbon can persist in these fluvial deposits, granted at low abundance, but despite the really harsh oxidizing conditions. So this suggests that ancient fluvial deposits on Mars may also retain traces of organics, which is really interesting. Moving out into the solar system, Titan is a moon of Saturn, which is a really fascinating world because it's the only other body in the solar system that has an active hydrological cycle. So on Earth, our hydrological cycle consists of liquid water, which we obviously have collected on the surface in the form of oceans and lakes, and then it can also rain down from clouds. On Titan, it's so cold that it actually rains liquid methane and ethane, which exist as gases here on Earth. And we also know that this liquid methane and ethane concentrates on the surface in the form of lakes. Unfortunately, though, Titan is also covered by this really thick atmosphere, so we can't use visual imagery to see what the surface looks like. So, in the 2000s, NASA sent a Cassini-Huygens mission. Well, it was a mission called Cassini-Huygens, and it was fitted up with a radar to try and study the surface. And we know that Titan has extensive dune fields, but unfortunately the radar instrument on the Cassini-Huygens probe wasn't high resolution enough to study them in close detail. So we didn't really have a good picture of the morphology of these dunes, what they looked like. However, in 2016, Paiu et al. Found a way around this by flying radar instruments over dunes in western Egypt and Namibia to glean more information from the radar data that we got back from Cassini. And they also flew an analogous radar instrument over mega yardings. Does anyone know what a yarding is? Yeah, it's kind of an underground geologic feature, but this is what they look like. They basically look like linear sand dunes. So they form in flat regions where there's really strong wind that flows in one direction. And what happens is the wind erodes the unconsolidated loose material on the surface and leaves behind these consolidated, cemented together structures that look like sand dunes. And what Paiu et al. Found is that the linear dunes encountered on Titan are likely to be of both Egyptian and Namibian type. And they also showed that radar features in the Cassini data looked exactly like what their radar features looked like going over mega yardings in Namibia. And something interesting about mega yardings is that a lot of them require interaction with liquids to form. So if you think of like playing with sand at the beach, and if you get the sand wet, if you let it dry for a bit and you start to poke at it, it's a little bit tougher. And so just like that, on Titan, this led scientists to believe that lakes of liquid methane and ethane used to exist closer to the equator to form these mega yardings, whereas now we know that they only exist near the poles. So climate change happens on Titan too. It's just not anthropogenic. So another cool icy moon is Europa. Europa is a moon of Jupiter that has a really thick ice shell underlain by a global subsurface liquid water ocean. And so this layering is analogous to ice shelves in Antarctica and Greenland, which have ice layers that can be hundreds of meters to kilometers thick, overlaying the ocean beneath. So scientists at Cornell, this is actually my research group, Dr. Brittany Schmidt's research group. I'm not part of this. I haven't been able to go to Antarctica and Greenland, unfortunately. But what our group does is they developed this robot called IceFin that they deploy beneath the ice shelves in Antarctica and Greenland to characterize the ice-ocean interface and melting dynamics on Earth as an analog for processes that might be happening on Europa. So here's a video of the team setting up their camp in Antarctica. I believe this was back in 2018. You'll see that they set up this A-frame that they used to lift IceFin up, and they had to drill a borehole to go through the hundreds of meters of ice. And as you'll see, they lift IceFin up vertically, and then they deploy it down through the borehole to reach the ocean, and this is what IceFin sees as it's going down. And once IceFin's down there, scientists up top can actually control it with an Xbox controller and swim it around. So IceFin has a sonar, it has cameras for video and pictures, and then it has a bunch of other instruments to learn more about the properties of the water here and try and characterize the melting environment. And so our hope is that one day an instrument like IceFin will be used to go to Europa or other icy moons like Enceladus to learn more about the oceans there. And since this is my group, I wanted to show a few more pictures. So on the left, this is my friend and colleague, Veronica Hegelein, driving IceFin and feeding it tether because IceFin is connected to a tether so that it doesn't get lost. And the middle is our team posing with IceFin before it gets dropped into the borehole. You can see that IceFin is really long. It's like 2 meters long. And on the right is my friend and colleague, Daniel Lean, minding IceFin's tether during a dive, making sure that it doesn't get tangled, because if it does, you're in for a world of hurt and hours of untangling it, which is not fun. And you'll see that while Daniel is sitting over the borehole, he's actually strapped into a chair, because you do not want to fall down a borehole. That would be really bad news for you. And we make sure that that doesn't happen in the field. So obviously, it's super fun as scientists and engineers to be able to go to these really remote locations to learn more about Earth and do new exciting science about other planets. But we don't always have to go to these faraway places to do analog science. We can also create analogs in the lab. So in 2008, NASA's Cassini mission sampled plumes at Enceladus, which is a small icy moon of Saturn. And they detected silica nanoparticles, which basically mean they determined that Enceladus has a rocky core in contact with the ocean, which is really important because it can provide nutrients and minerals that are usable by life if there are microbes swimming around in Enceladus's ocean. It's also important because since then, scientists have hypothesized that hydrothermal vents might exist on the seafloor of Enceladus. And this is important because hydrothermal vents may have catalyzed life on Earth. And so scientists have since recreated hydrothermal vents in the lab at Enceladus-like conditions to determine if they're a usable source of energy for any life that might exist on Enceladus. So this photo on the bottom left is an artist's rendition of Enceladus. It has a bunch of plumes spewing out from its south pole. This middle image is a hydrothermal vent called a black smoker that exists on the seafloor of Earth. And then on the bottom right are an example of hydrothermal vents at Enceladus conditions that were made in the lab in Dr. Lori Barge's group at the Jet Propulsion Laboratory in Pasadena. So hopefully I've given you all a wide variety of examples of different places we can go to on Earth to learn about planets from Mars to all the way out at Saturn. Now, I also am an analog scientist, so I wanted to spend the rest of the talk talking about the analog work that I do and how I incorporate it into my PhD research. So as Alina said before in the introduction, I study landforms called pingos, which is a really cute name for hills of permafrost and ice that only form in permafrost regions on Earth. So these primarily exist in the Arctic, and there are also some in the Antarctic. Pingos are really unique surface features. As you can see, the tundra is really flat, so when you have these hills just protruding up from the ground, they're really easy to spot. They're also reservoirs of really abundant ice in the subsurface, and they take lots of groundwater to form. And they're also hotspots for microbes. So the Canadian Arctic in the summertime looks like this. It's pocketed by these transient lakes called thermokarst lakes that form when the active layer, or upper few meters of permafrost thaw in the summertime. However, in the summertime, these lakes can also catastrophically drain into unfrozen saturated sands called a talc. And then when winter rolls around again and temperatures drop, the talc would begin to freeze from the top down and from the outside in. This creates a buildup of hydrostatic pressure, which pushes groundwater from the pores of the talc and concentrates it toward the center of the drained lake basin. And since ice is less dense than liquid water, we know that liquid water will expand volumetrically by about 9% when it freezes. So that volumetric expansion works in tandem with that hydrostatic pressure to basically uplift the surface and create this little hill when it freezes. And that's what we call a pingo. And with time, pingos can grow in height as more groundwater is added to the system via seasonal freeze-thaw processes. And when pingos get really old and the ice core gets big enough, it can actually rupture the overlying surface and you'll get something that looks like this. So this is Ibiak Pingo. It's the second tallest pingo in the world at about 50 meters high. And this is a perfect example of what pingos look like when they're mature. Now, the reason that pingos are a good analog is because we also see evidence of pingos on Ceres and Mars in regions where abundant liquid water once flowed through the shallow subsurface, which we know we need a lot of to create pingos. And as you can see, if you compare potential pingos on Mars and Ceres to Ibiak Pingo on Earth, you'll see that they're very similar shapes, and they also have similarly fractured surfaces. So they look a lot like pingos. But unfortunately, we can't go there and study them. And thus, the Pingo STAR team was born. This acronym stands for Pingo Subterranean Aquifer Reconnaissance and Reconstruction. My advisor is really good at putting acronyms together. And the key objectives of this team are to, one, map the surface morphology, or basically what the surface looks like of pingos, map their internal structure, basically trying to figure out how much ice is inside these pingos, and also their deep hydrology. So how are pingos connected to the groundwater environment? And we did this using 3 different non-invasive geophysical instruments. And in doing so, we assembled a large data set of multiple pingos, all at different stages in their life cycle, to compare and contrast their structures. And all of this was to learn about the pingo formation and evolution process on Earth, but also to help constrain the formation conditions, processes, and properties of potential pingos on Mars and Ceres. So to do this, we went to Tuktoyaktuk, Northwest Territories, Canada, which is right on the coast of the Arctic Ocean, and this region also has the largest concentration of pingos in the world, so it was the perfect place to go. We conducted surveys over 9 different pingos in the Pingo-Canadian landmark. And now I just want to talk you through the different instruments that we used and what we got from each of them. So the first instrument that we used is a ground penetrating radar, or GPR. And what this instrument does is it sends radio waves or microwaves into the surface that bounce off of layers that are made of different materials. So we would drag the GPR over the pingos and essentially get a picture of what the internal structure and stratigraphy looked like of these pingos. Doing fieldwork here was quite the workout, because if you imagine doing fieldwork in the Arctic in March, it was very cold, very windy. We were carrying several pounds of winter gear on ourselves to keep us from getting hypothermia. And then we had to hike over these super steep hills in big boots in snow that could be more than like a foot deep. So it was type 2 fun, which you can look up what that is after. The second instrument that we used is a capacitively coupled resistivity instrument, or a CCR. We operated this in the same way as we did the GPR, so by dragging it over the pingos. But the way that this instrument works is it injects a current into the ground and then measures the resulting voltage that the ground responds with, which basically is to say that it can tell us whether materials in the ground are resistive or conductive. So resistive materials are like pure ice or snow, and conductive materials are like liquid water and salt. So the GPR gives us internal structure and stratigraphy, and the CCR gives us the composition of those materials. So we can use both of those in tandem to get a fuller picture of what the inside of pingos look like. And the last instrument we used is a transient electromagnetics instrument, or a TEM. This one was the easiest one to operate, thank God. We would basically set up a big loop of wire on top of the pingos, and this worked very similarly to the CCR. So it would inject a current into the ground, but this one was a lot stronger. So using the TEM allowed us to probe really deep, so we could get resistivity measurements about ground that was 100 meters deep from where we were surveying from. However, since the TEM was taken in one place, we lose that lateral information that we get from dragging the instruments over the pingos. So this is what we use to try and get at the deep hydrology of the pingos and what's going on dozens of meters beneath the surface. So I just kind of wanted to show you guys what the data from these instruments look like. So I'll take you through these different plots. Again, this is a top-down view of Ibiuk. This flank of Ibiuk here has a lot of mass wasting, and it's extremely steep, so it wasn't safe to survey over. So you'll see that our survey line just went halfway up the Pingo to the depressed summit, and this star is where we collected our TEM profile. So this right here is a radargram, which was what we get from the ground penetrating radar. These really bright regions are called like scattering zones, and these are where there are really stark differences between the overlying material and the underlying material. This is our CCR data. So yellow regions are more resistive, like ice, and blue regions are more conductive, like sea ice that has a lot of salt in it. And this is a TEM profile, which basically tells us the resistivity at different depths. So now I'm just going to point out a few different features. Right here, about 20 meters below the surface, we see this bump in resistivity. And at the same depth in the radargram, we see this big honking lens-like feature, which looks a lot like a massive ice core that we would expect to see in pingos. So that's exactly what this is. The GPR data looks a lot like massive ice, but we can't really determine if it is massive ice for sure unless we have some compositional information as well, which is what the TEM gives us, which is an example of why we need all of these instruments working together. This is where the ice core would be in the CCR inversion, but unfortunately it was deeper than our instrument could probe. But lastly, the CCR does have this really interesting resistive blob that seems to protrude from the depths, and that's met with this radar transparent region, which, sorry, it's a little small on the screen, but you can see some uplifted layers. So using these two pieces of evidence together, that also tells us that not only does Ibiak have a massive ice core, but it has these really massive flanks of ice on its periphery, which isn't something that we expected, so we learned something new. And next, just to give you a sense of the different pingos that we were looking at, these are data collected on Split Pingo, which is the second tallest pingo that we surveyed. And you can kind of tell just by looking at it that it looks very different from Ibiak. And the biggest thing that we learned from our fieldwork is that no two pingos are alike, and the data that we collected looks so different from every single pingo. However, Split also has this resistive anomaly, but then if you look at the radargram, it lacks that really big ice core that Ibiak has. So that's something we're trying to figure out. We think that Split might be older than Ibiak, and so its ice core is actually farther along the path of receding. However, just like Ibiak, Split also has these massive ice wedges on the periphery. So this is really cool stuff, and we've learned a lot about what the insides of pingos look like. But at the end of the day, I am an astronomy PhD student, and I don't think my committee would let me graduate if I just did Earth stuff. So where does the space element kick in? This leads me to another one of my projects, which is to assess the likelihood of pingo formation on Ceres. And I use the field data that we collected in Tuktoyaktuk to help guide the analysis of my results. So, Ceres, for those of you that might not have heard of it, is a dwarf planet in the asteroid belt between Mars and Jupiter. And I'm a little bit biased, but the most beautiful dramatic feature on the surface of Ceres is Akator crater, which is shown right here. Akator crater is an impact crater that has a bunch of bright salt deposits. And these salt deposits are evidence of brine flowing through the shallow subsurface. So just like Badwater Basin, where you have a bunch of salty water or brine on the surface that then evaporates away and leaves the salt behind, this is what we think happened at Akator. But really interestingly is that the floor of Akator crater is also home to hundreds of hills and mounds that look just like terrestrial pingos. And so scientists have put forth a hypothesis for how they think these mounds were formed. Basically, when impact craters are formed on planets, the impactor deposits a bunch of heat into the ground. So not only does all the subsurface stuff kind of get blown up into space, but it also melts a lot of the subsurface. So on Ceres, this created impact melts with a bunch of water and clays and salts. And so as these impact melts were sloshing around the floor, eventually they come to a halt and start to freeze from the top down. So you have freezing that generates pressure gradients, and you have a bunch of groundwater flow, which, as we know, are the ingredients for making a pingo on Earth. So maybe this is enough to create pingos on Ceres. But why do we even care if there are pingos on Ceres? Who cares? Well, there are a couple reasons. As I was saying before, pingos are reservoirs of abundant ice in the shallow subsurface, and we know that on Earth, they're hotspots for microbes. So, if we ever want to send another mission to Ceres to maybe assess its astrobiological potential and see if there are any habitable regions, pingos are really excellent candidates to look for that. Alternatively, if we ever decide to put human boots on Ceres or Mars, and those astronauts are in a really bad situation and need to find a bunch of ice to melt down to drink, pingos are a really great place to go to utilize their resources. So how do I actually test this? I use a thing called numerical modeling, which is a piece of jargon that I will explain. But basically, the field work that we do in the Arctic allows us to get a really thorough picture of what pingos look like at one point in time. But numerical modeling is a tool that allows us to simulate pingo formation processes over really long timescales and in environments that we can't find on Earth because they're too extreme. So basically, I simulate heat transfer and groundwater flow through impact melt deposits on the floor of Akator crater to see if pingos can be formed there. And one of the worst parts about being a planetary scientist is that we just don't have a lot of data about planets, especially the insides of planets. So I have to test a wide variety of parameters to see which subset of parameters are favorable for pingo growth. Luckily, NASA did send a mission to Ceres called Dawn, and since Akator crater is so cool, we collected a lot of data there in terms of visual imagery and also some compositional information about the shallow subsurface. So these parameters that I'm testing do have bounds, things like salt concentration and porosity. So I do have a starting place, but there's still a lot to test. And then after I have the results of my numerical models, I can use our fieldwork data to help interpret the results and assign them some meaning. So the way that numerical modeling works is step one, you have to create a model domain. So this is a self-contained impact melt deposit on the southeastern part of Akator crater. And I chose this region because it has 20 really good pingo candidates. And it also has its own bright white salt deposits. So we know that there was once a lot of liquid water flowing through the subsurface. I also assigned a depth of 600 meters to this impact melt deposit so that I basically have a box that the physics happens in. And the second step is to then assign input parameters to your model domain. These are things like porosity of the ground, salt concentration in the liquid water, heat flux coming from the planet, and other things. And it turns out that porosity and permeability of the subsurface are the most important parameters because if rocks are more permeable, this allows more groundwater to flow through it, which is really important for making pingos. And then lastly, once I have my model domain and I have all of the input parameters, I then choose my relevant physical equation that I want to use to advance the system in time. So don't try and make sense of these equations, don't let them scare you. I just wanted to show you the equations that I use to guide my numerical simulations. So on the top, this is a three-dimensional equation that describes how groundwater flows through a porous medium. And then the bottom is a one-dimensional equation that describes heat transfer through rocks. And then once I do my model runs, I'm able to see how much water is delivered to each potential pingo in our model domain. So this is an example of one of my cases that I was testing, and the dots are the different potential pingos, and you can see that each of them receive different amounts of water. However, it doesn't really matter how much water they get. What does that really mean? We need to try and make sense of that to see how that correlates to whether or not it's likely to be a pingo. So what I did is I looked back at our field data, and I was able to calculate approximately how much ice is in the subsurface of each pingo. And while it varies, I found that each terrestrial pingo has anywhere from about 10 to 90% ice, meaning that for each pingo volume, 10 to 90% of that volume is occupied by ice. So I could use that to apply to the results and kind of filter out which hills I think are most likely to be pingos, and also which cases have the most amount of pingos, which will basically tell me, okay, pingos can only be formed here if it has a porosity of 35% or more, for example. This is still a project that I'm working on, but in general, results suggest that it seems to be very, very easy to generate water to form pingos. But quite annoyingly for me is that in some cases it seems like you form way too much water, so you would expect to see geysers coming out of these impact melt deposits in some cases, which might not actually be too far from reality because Akator does have a lot of salt deposits on the surface, so that liquid water had to come from somewhere, right? So bringing it all back together, I think that analog science is one of the best forms of science to do, and it's one of the funnest for sure, because not only are they really beautiful places to visit, and not only do they help us understand other planets while learning more about our home planet, but they also connect us to really awesome people who are stewards of the land. Sorry. And so not only is the science important, but the knowledge that we learn about the cultural significance of the landforms and places that we're studying and how the landscape has evolved through the eyes of people who have lived there for hundreds, if not thousands of years, I think is even more important than what we get from the science. So our fieldwork in Tuktoyaktuk definitely would not have been possible without the citizens of Tuk. They housed us, they cooked for us, they guided us in the field, they helped tell us how these pingos have changed over the past several generations. And so I just wanted to give them a shout out and thank them for enabling this really cool science to happen. And that's all I have for you. Thanks so much for listening.
All right, thank you so much, Alexia. So now is the time for any questions. So it's a Q&A. I will run the mic over to you so that people on the Zoom can hear. And if anyone on the Zoom has questions, I've enabled chat, so you can drop that in the chat. Did you have a question here? Okay, awesome.
Hey, I'm trying to understand why the pingos are hotspots for bacteria. Can you contrast the pingo to the land next to the pingo, and why would the bacteria be more in the pingo?
Yeah, no, great question. So I didn't harp on that too much because it's a bit of a looser connection when it comes to tying terrestrial pingos to other planets. But something about permafrost is it has a lot of methane in it. And there are specific microbes called methanogens or methanotrophs that either eat the methane or create the methane. So there have been studies of the permafrost that pingos are made out of, or even springs of water that come out of pingos, and scientists have found that they have a disproportionate amount of methanogens or methanotrophs. So that's kind of the idea, is that we know on Earth that there are specific microbes that choose to live there because it's a really good environment for them. I'm not a biologist, as you can tell, which is just like another key that this could be a really important astrobiology tie if there's another planet that has evidence of pingos that might also have methane or other nutrients that microbes could use.
But compared to the ground right next to the pingo, would there be any difference in the bacteria?
I don't know. I don't think there's been a study comparing. Actually, I do know of one that is in prep comparing pingo microbial communities to the surrounding permafrost, but I haven't heard of any results from that yet. So that's still an ongoing study. So I can't really give an answer for that of what I would expect the differences to be. Yeah.
Does anyone else have any other questions? Yes.
It was very nice to hear, and I remember hearing about pingos when I was in graduate school a long time ago, but very little was known about them, except that they were being thought of in those days very early on as maybe analogs to some things that have been seen in some of the Mars images. Do you get any feeling from the people you talk to there how old these things are? Do they live for decades or centuries or millennia, or do you have no idea at all?
Yeah, so Ibiak pingo, which I've shown many pictures of, is definitely the most studied pingo in the world. And basically, we think that it's been around for well over 1,000 years. That number was kind of arrived at from two different angles. So one, there's a scientist called John Mackay who studied the pingos in Tuktoyaktuk for decades. They were like his magnum opus. And he used thermodynamic arguments of how the permafrost would degrade in these zones, that it would take 1,300 years plus or minus 200 years to create something the size of Ibiak. And then a little later on, there was a study doing radiocarbon dating of a bunch of different constituents of Ibiuk, and they came at that same number of around 1,300 years. So yeah, Ibiuk is probably in that ballpark, but it totally, the lifetime of pingos can change depending on like the amount of ice that is there to begin with. And also if there's like a really hot year, that can trigger thaw of the ice core and then lead to pingo collapse. So there are a bunch of other factors too that impact the lifetime of a pingo, but it's hundreds and hundreds of years.
Anyone else? Come over to you. Here you are.
Yeah, so when you're looking at the porosity of the rock for like water flow, how do you determine what porosity is like the most likely to be on the surface of Ceres or other like planetary bodies?
Great question. So people have analyzed in very close detail the visual imagery that we've gotten from Octor crater, and we can see how the impact melts have flowed. And we also have some information on the composition of the shallow subsurface. And scientists have come to a consensus that the impact melt themselves are basically slurries of like clay. And that also checks out with what we know the bulk composition of Ceres to be. So what I did is say, okay, we know that these impact melts are clay-like. What's a range of porosities of analog clay-like materials on Earth? So that's what I used, and then I just kind of went from there. So I test from like 25 to 65% porosity, which is a really large range, and that's guided by the range of clays found on Earth. But again, you don't want to be too restrictive with what you're doing because at the end of the day, we don't really know for certain.
Any other questions? Okay, we do have a few questions from the Zoom, so I'll read those out. The first one is, can extremophile organisms possibly exist within pingos on other planets?
Yeah, great question. So that's kind of what we were talking about earlier. Maybe. If that planet also has other things like energy to support life and nutrients to feed life. We know that there are microbial hotspots on Earth, so in theory, if another planet has all of those same ingredients, probably. But we definitely don't look at these potential pingos on Mars and Ceres as, hey, let's definitely go there to look for aliens because they're totally there.
Okay, the other question that was on the Zoom is, can you provide some other practical examples of using analog studies?
I'm not really sure. I tried to supply lots of practical examples at the beginning. We can go there to basically use like geophysical instruments to try and see the internal layering and compositions of these surfaces to help us figure out if surfaces on other planets look the same. There's also like the Iceman robot again, which looks at the ocean specifically to see what those ice-ocean interactions, which are directly analogous to icy moons that are very inaccessible to us, might be like. So maybe if they could be a bit more specific, I'd be happy to expand more upon that.
Does anyone else have any other questions? Okay, I have a really quick question. Is the much lower gravity of places like Ceres something that you have to account for when comparing potential pingos there to pingos on Earth?
Oh my gosh, what a question. Yeah, that's something I think about a lot. So when we're thinking of groundwater specifically, it depends on something called hydraulic conductivity, which depends on the acceleration due to gravity of the planet that it's on. So that totally impacts the speed and the volume of groundwater that's flowing through the impact melts on Ceres, which is something that I have applied to my model, and I'm still working out on how big of a parameter that is. Also, gravity on Earth leads to compaction, so as you go to deeper depths, there's more pressure and the rock gets more compacted. But on Ceres, the gravity is so much lesser that at depth, the rocks aren't going to be as compacted as much, which again has implications for groundwater flow, that you might actually get more flow at depth that could still be connected to pingos on the surface than we would expect on Earth. So those are some examples. Yes, it's definitely a factor.
All right, awesome, thank you. If we don't have any more questions, do you have a question? No? Okay. I'd like to thank you all so much for coming. If we could get one last round of applause for Alexia. All right, awesome. Just as a quick reminder, if you guys are interested in attending any of our other lectures, the schedule can be found under events on our website. And as always, Fuertes Observatory will be open tonight from 8 p.m. to midnight. So thank you all for coming.